My project is about hardware-assisted smart quantization of normalized DNNs. I'll start off with a little bit of background on deep neural networks and deep neural network training. Um, as I go through this, just one thing I wanted to mention is usually when you see sort of figures of neural networks, you see this picture on the right. Um, when I'll be showing any figures or things like this, I like to think about it as the picture on the left, which is a computation graph. The picture on the right, really all it's doing is two matrix multiplication. It just looks cooler. But for our purposes, the representation on the left is much more valuable, and it also shows exactly all the sort of different elements. So W and B are the weights, X is the input, and so on and so forth. We're focusing on compression of DNN data structures. So I'm just going to go through the data structures that we're going to be compressing. The weights are the parameters of a layer. Essentially, you can think of a deep neural network as this f of x could itself be a neural network. It's a very long chain of computations that at the end generates a loss. Weights are going to be the parameters of each computation that you go through. The feature maps are the intermediate values. So in this figure, the f of mv, f of uv, and f of u, these are the intermediate values, and they're called feature maps. The gradients are the gradients of the loss with respect to the weights. This is an important distinction. It's not with respect to the inputs, because we can't really change the inputs. We're changing the weights. So in our case, if f of x is the loss at the end of the day, then the df, dw, and df, db are gradients. One thing that's important to keep in mind is notice how f of x actually shows up in these two different gradients. This is what we like to call a featured or a stashed feature map, and this is a memory cost because to be optimal, we have to save this computation so we don't have to do it again in the backward pass, and so that's a memory cost, and this is one of the reasons we're going to be compressing these data structures. Finally, gradient maps are kind of like feature maps, but they're the intermediate values for computing the gradient. Now I'll go into batch normalization. So the equations here essentially explain batch normalization. It's a very popular technique that's used in ResNets, it's used in transformers. Most popular networks out there use some sort of normalization. Essentially, they're used to make DNNs more stable and faster. Not really sure why it works. There's different theories, but it does work. And the idea is essentially xi, which is sort of but basically you take the input, the x hat is the z-score of that input, so we normalize it, and then we end up shifting and scaling the normalized value, which is this z-score. And this gamma and beta, they're parameters that we learn over time. Recent research has showed that batch normalization is very powerful. So there's a paper in iClear in a week. Basically, they show that just training batch normalization parameters and leaving everything else randomly can reach 82% accuracy in C410, which is very impressive. Now the final piece of background is just my prior work. So I worked on a method called smart quantization, where we essentially we observed, and you can see in this first figure, that a lot of these different data structures, if you actually look at their distributions, they're very normal in nature. They're clustered around the mean. So we came up with a compression method where we first normalize these inputs into their z-score values. As you can see, this is the first step in the normalization. Then the z-score values, because they're now if they're normal, they have to be between -3 and 3, for example. That's a sensible range of standard deviations, so we can quantize them very easily. What we do is now we use the intuition that maybe things within that cluster need less bits and outliers should get more bits. And so we quantize the normal values within one standard deviation to 6 bits, and the rest get 8 bits. And this is an example of that running. So now the new work here is now we want to extend this to batch normalized neural networks, and we want to implement the sort of hardware for it. So essentially what we're doing is we want to account for these batch normalization parameters in our algorithm. And effectively what this could be used for is replacing the batch normalization layer altogether. Because if you noticed, our method is very similar to batch normalization. The only thing that it lacks is that gamma and beta parameters. So we could just completely replace those layers and replace it with signals to the GPU saying, hey, you should store this using this compression technique. This is the same step-by-step, but now I've outlined exactly what changes. So only additional step really is shifting and scaling the z-scores based on these two parameters, gamma and beta. And the sensible range still stays, but it's shifted by the gamma and beta values. And this is the same sort of process. So we take the z-score, then we normalize that z-score, and then we quantize it again. just as we did before. So now I'm going to go through some basic optimization. So for calculating mean and standard deviation, those turn out to be the bottleneck in our computation. One of the basic optimizations is just using an alternate variance formula, where instead of having to do x minus mu at every step, you could actually just do get the mean, subtract that from the expectation of the x or expectation of x squared, and these are sort of mathematically equal. That gives us a little bit of optimization. There's a paper called Scalable Methods for 8-Bit Training of Neural Networks. They proposed an approximation for standard deviation called range standard deviation. And this is another optimization. They showed some bounds, but we'll see in the results this doesn't turn out really well for us. And finally, the sampled statistics, where instead of taking the mean and standard deviation of the entire input, we just do it, let's say, for a sample size of 16. Okay, so you have two different sort of experimental methodologies. The software is we essentially implement a framework that simulates the inaccuracy of compression. We do this by compressing and immediately decompressing, and we also take in the batch normalization into account. These are the results. So I've compared them actually to networks with different encodings. So BF16, FP16, FP32, and FP8 are popular floating point formats. Shifted and squared FP8 is a paper that got accepted into iClear 2020. And that's another one that we wanted to compare to. And SMAQ is our original method, and the batch normalized support, as we see, does better. And out of all of this, our method does the best while maintaining a very good accuracy, very, very close to BF16 and FP32. For the hardware implementation, we use the Vivado HLS to implement the sort of IP for it. I wasn't able to implement the end-to-end sort of simulation of the neural network training, but we took some performance utilization and power estimates of this accelerated module, and we tried these different optimizations to see sort of how it pans out. The results here, essentially, to narrow things down, obviously the base is the most simplest one. The base is when we don't even calculate the mean and standard deviation. We take those as inputs. If we start calculating the mean and standard deviation, that actually ends up increasing our sort of estimated latency by a ton. And if we, obviously that's reduced if we take the sample. The range standard deviation, the main thing that I noticed is it decreases the number of DSPs that we use, but on the other hand, we have a lot of lookup tables and flip-flops that we use. The conclusion really is this method can reduce the memory by up to 4.92 times with minor impacts on accuracy. That we also learned that if we compress away the batch normalization layers, we actually are able to do better. Finally, in the hardware implementation, the primary bottleneck is the statistics calculation, sample statistics reduces our resource utilization and latency, but doesn't. The impact on accuracy was about 7%, and range standard deviation doesn't actually produce very accurate results. And if I were to go back in the software results, it is down to 70, which is a good 17 points below the normal. And the code for all of this, including the hardware implementation, the software simulation, and everything else is on GitHub. Feel free to ask any questions.
Thank you. What was the result? Was it for net or was it for 10? Or, yeah. Okay.
Yeah, so this was ResNet 34 on CFAR 10. Primarily, I've only implemented this for batch normalization. There are other normalizations such as layer norm, and instance norm, and I haven't really implemented those. In this case, I've kept it strictly for ResNet and CFAR 10.
And the latency you show was the compression or decompression?
This was the compression, but because the compression and the decompression and the compression logic are very similar, with the exception of the statistics stage. So the results for the base would exactly be kind of the same thing in decompression.
Is it possible can be parallelized even more?
So this is actually a slide that I've hidden. There's a bunch of optimizations that I was able to implement, there's a lot of parallelization that I was able to do using this HLS pipeline, HLS data flow, and the unrolling. And so there's a lot of optimization already there. The main bottleneck is in the statistics stage, and I don't really know. I'd like to see. Well, that's an area I wanted to research more to see how I could parallelize that calculation of the mean standard deviation even more, or something of that nature.
All right, thanks.
Mhm.
Thank you. And questions?
Where is the hardware located? Is it implemented as a execution unit or as an accelerator, something like that?
Yeah, so right now, really, these are sort of performance and latency estimates from just the IP itself. Ideally, this would be an accelerator, maybe a sort of modification. Well, one of the ideas was I would have taken Vortex and sort of tried to add this to the OpenCL as a fixed function accelerator. But based on the time and so on, it wasn't feasible to go with that end-to-end simulation. But I think that would be probably adding it as a part of the GPU. I think that might be the most realistic way.
Thank you.
And just a question, like I know you said that you've only simulated the IP, but finally, if it's on the GPU, do you see having like one of these IPs for a bunch of SMs on the GPU, because or do you think it's necessary to, like, because I'm assuming every layer would require batch now, so do you?
Yeah, no, that's a good question. I think I probably having it on every SM makes sense. I'd have to I guess what I'd like to see right now is how are some of these accelerators currently added, because essentially what we're doing is it's a memory compression technique, but by the virtue of similarity, it's also batch normalization. And so I'd like to see, I guess, how do some research on how the specific layer accelerators are added generally. I know for example, CUDA NN that NVIDIA has, and I'd implement it in a similar method if that means that in every single one of those SMs or in the tensor cores having some sort of resources for that may be the way to go.
All right, thanks.